Good morning. I'll be talking today about trying to summarize fire prediction and mapping. So the business of this begins because we have about 80,000 fires in the United States a year, burn to 4 to 10 million acres a year, including Alaska, somewhere in there. 95% of this area is burned by only 3% of the fires because we primarily suppress the other ones. Fire response is multi-agency, all hands, all lands. All of this fire has created a great deal of demand for many, many decades, as Steve Pine indicated, for prediction and for mapping. These are some of the tools. I'll be going into each one of these in detail over the next. Just kidding. But there are many systems, models, tools, data, and maps. I'm just going to make a few points about this cornucopia of different systems. Prediction. So prediction, basically, that's modeling. That's how we do the prediction. Different time frames, different spatial extents. The main areas in prediction are operations. That includes active fires, primarily predicting where they're going to go, planning, doing risk analyses, fire management plans, fuel treatment analysis and design, training. Fire prediction is all part of how we train firefighters to be safe on the fire line. And of course, research, different kinds of ecological models. The basis for all of this in practice in the United States is the Rothman spread equation, published in 1972, but which was a culmination of about a decade or more of laboratory and field research in Missoula. It's got very practical inputs. It's fast. It produces fairly reasonable outputs, despite the fact that it's got major limitations. The data, the kinds of data, the detail that can be ingested, the behavior of the fires that can be simulated, and the fidelity with respect to the actual fire. In the old days, good old days, before computers, people used maps, and they used nomograms, and they calculated spread rates, and they vectored slope and wind effects to produce a fire growth map. These days, what we use is a system, probably the best developed one is the Wildland Fire Decision Support System, built in 2009. All federal fires are contained in this. They have to be entered. It provides access to models and data and decision framework. Different kinds of modeling. You're seeing fire growth projections and fire behavior calculations, probabilistic kinds of predictions that can all be overlaid with values at risk. So you're seeing here is a probability of impact for a given wildland fire, overlaid with homes, power lines, ownership, habitats, bridges, gas lines, all sorts of stuff. That gives you a true risk framework. So the advantage of having a system like this is we can compile statistics on usage. The number of analyses in the 8 years of operation has been 43,000 analyses for about 4,000 total fires. That's about 500 per year. Given the total number of fires in WFTS, what that means is only about 3% of the fires on federal lands get any kind of analysis. It's not coincidence that those 3% are the same 3% that burn 95% of the acres, okay? Because we put out all the rest. There's no point in modeling fires that don't spread. But as a percentage of all the fires in the United States, it's less than 1% gets any kind of modeling support. Other analyses in the planning phases, basically this is just one example, but risk analysis. Monte Carlo simulations of thousands of tens of thousands or millions of fires over many different synthetic years allows us to look at probability distributions of fire behavior and calibrate these things with observed. This is one example of the amount of computational effort that goes into this. This is a national burn probability map composed of simulations done piece by piece, tile by tile, and then put back together. 94.5 million fires were going into this. The Wildland Fire, the National Fire Danger Rating System is another analysis that's produces many different maps daily and multiple times a day. It's accessed through the Wildland Fire Assessment System. We're familiar with the fire danger rating categories. At the heart of all this is the Rothman spread equation as well. We have fire effects. At the stand level, at the multi-stand level, at the landscape level, we have analyses that incorporate fire behavior and fire prediction to understand what consequences they're going to have, how to design fuel treatments, et cetera. So a summary of the modeling business is basically that operations, even though that gets all the news and it hits all the headlines essentially, is less than 1% of actual modeling. Most of it is in what you might call planning. I don't have figures for research. Research certainly would be in there, a lot of ecological modeling going on, but you get the picture. Most of the fire modeling going on in the country is not associated with active fires. There just aren't that many of them. In the decision space, what to do on those fires is very, very limited. by politics, as we heard earlier. Let's talk about mapping. Many different kinds of mapping. I'm sure your favorite product might not be on this list, but bear with me. We have fuel mapping. We have monitoring trends in burn severity, which you've seen examples of. Burned area rehabilitation uses this kind of information. Satellite fire detection, MODIS, VIIRS, and other kinds of technologies. Fire danger rating and airborne IR through the National Infrared operations. So land fire, everybody's familiar with. It's the basis for almost all the fire decision support systems in the United States. There's 20 layers of vegetation and fuel-related information, continuous wall-to-wall, updated every 2 years, sorry. AVHRR provides greenness information at 1 kilometer resolution. We have MODIS imagery, which helps us look at very large fires, and it's amazing detail. Okay, this is Rodeo Chetaskai fires in 2002, and you can see the fire actually growing. All those yellow lines there are fuel treatments, where you can see in a burn severity map, they actually are still amazingly green. Burn severity, there's a national program administered by RSAC and Aeros Data Center, monitoring trends in burn severity, mapping all fires greater than 1,000 acres in the west and 300 acres in the east. A lot of new technologies for remote sensing, a lot of it, numerical modeling, okay? So, what's holding us back? Why aren't we using all this stuff in operational predictions, okay? Well, I think the big thing is limited knowledge. We still don't know how fire spreads. That's really a very basic question that we should be able to answer. But if you don't know how fire spreads, then essentially you can't take advantage of all these data collection techniques through remote sensing. Even our physical models and our empirical models, for sure, don't resolve the actual processes that produce spread. You can see that in papers like this. This is a summary of 19 different models. It's an interesting paper that compares them. These are all so-called physical models. Identification and formulation of the processes involved in the behavior of wildland fires is problematic. Really. Physical models, but we can't identify the processes or formulate them in a model. Okay, have a look here. This was from Terry Clark et al. In 2003. The science of wildfires in its infancy. Numerical models are a necessary step towards wildfire prediction, but they face the enormous task of treating a physical problem where the relevant spatial scale spans 6 to 7 orders of magnitude. So, what fire spread is, it's a non-stop reaction involving combustion and energy release, heat transfer to ignite new fuels that feed back into the spread process, right? These are actually operating at sub-millimeter and sub-second levels. That's the challenge. Let's just look at how ignition takes place. See that fire there? Well, we can duplicate the radiative output from that fire with a simple chicken heater for a garage, okay? 37 kilowatts per meter. It'll fry your skin at second-degree burn in 1 second. If we understand fire spread so well, then answer the question, which one of these fine particles will ignite first or the wood block? Well, you'd be very surprised. The fact is the wood block will ignite in less than half a minute, and the Excelsior will not light at all. It'll sit there basking in all of that radiation. So if you're puzzled by this, well, we can have some questions about that. I'm going to leave you hanging. Thank you.